Hi, my name is Bianca Reynoso, and I'm going to be telling you a little bit about Benford's Law today. So, what is Benford's Law? Benford's Law is the probability distribution function of the appearance of numbers beginning with digits 1 through 9 among a random set. Pretty much this means if we have any set of given numbers that haven't been manipulated in any sort of way, we should see a general figure or curve that can be defined by this function. And this function can actually be computed in any base as long as the base is greater than or equal to 2. So for the definition, we have that if P of x has the set domain of numbers 1 through 9, the probability distribution function can be defined as this function right here. I'm going to do my best to read it out loud. It's going to be P of x equals log base b with argument 1 plus 1 over x, such that b is greater than or equal to 2. So the calculations that I did for this presentation are actually done in base 10. I double checked them with the Wikipedia source that I have at the end of my link, but given these numbers and this function, I have these results. And so we see that we don't have an even distribution of each number appearing. We have 30% of ones, 17% of twos, 12.5% of threes, and so on and so forth till we get to 4.6% of nines. The only number that has about almost a 9% chance would be fours or fives appearing, more specifically fours appearing, and this makes sense as far as how numbers work, but to the average person, me, I would think that you would have an even chance of seeing ones, twos, three, four, fives, sixes, seven, eights, or nines. But I am a bit of a hands-on learner. But before we get there, how is this relevant? Since this is a natural occurrence, we can use this law to spot something unnatural like fraud or false reporting. So found in the Data is Beautiful subreddit, user rdataartnjv beautifully compiled a graph comparing county-level daily COVID cases to Benford's Law. And see, here we have in blue Benford's Law and red COVID-19 cases. So the numbers being reported by each county, starting with each digit, follows this curve. This would further allow us to be confident in the numbers that are being reported as completely accurate. So can we try this at home though? Is this one of those things that you need to work in a lab for, or that you need a lot of experience to prove? But it's fairly easy to do at home. So in order to get less divergence from the desired curve, we're going to need a large sample size. So ideally you'd want to use a newspaper of the Financial Times or something with stocks, something with a lot of numbers that has a lot of percentages, prices, a lot of data to work with. But the numbers that you don't want to include are going to be phone numbers, dates, heights, anything with a confined set range. This is because if we do it for heights, for example, we'll see that the average height is going to be like 5.5 feet and 6 inches for just a general person. But we don't actually have people who are 1 foot tall or 2 feet tall as common as we would have someone with a 5'5". So it's a little bit more difficult once you get to constrained ranges, but it can still be done with a larger range of numbers. I didn't have a newspaper at hand, so I used this Costco Connection magazine, and there are not a lot of numbers in this magazine, but with the numbers used, I tried to compare a couple different ways of going about trying to prove this law to see if it holds up. I'm a bit of a hands-on learner, so after tallying up the appearances of each number, I used Excel to compute a probability for each number like so. Pretty much, the way I got each percentage was I used the number of appearances over the total numbers in a set. So, only using the prices and percentages from each page in the whole catalog, essentially, we see that we do have an uneven distribution with a skewed left graph. But we do have some inconsistencies such that there's a large difference between 1 and 2, but there's more 3s than there are 2s. It doesn't change in the same way a Benford's Law curve would actually change. So we see that this isn't exactly a really good representation of what we could be seeing. This could be for many reasons. One, that there's not enough numbers to work with, or that the numbers being presented have a little bit of commonality. For example, there seems to be a sale with a lot of $3, $4, and $5 off. So I can see how those would add a little bit extra, but we do have a little bit of inconsistencies here. Once I started using any number that I saw, pretty much excluding only item numbers, dates, phone numbers, there weren't really any heights or weights in the magazine, so there wasn't really much to exclude that way. But as soon as I started including a lot more numbers, I had 963 numbers and 283 ones out of everything. The nines, I only had 21 nines. And beautifully, I got this curve. While it isn't completely there. It's not as close as we'd want. We can definitely see the curve happening. We can see the change happening within each step or digit to be observed. It's not quite as clean, but I imagine using a lot more numbers or maybe doing 2 or 3 catalogs, we might get a lot better of a curve. And so for my references, I did enjoy the number file and singing banana video. They did a really good job of explaining it in a way that was pretty understandable. I didn't use these two as heavily as I did the other videos and this chart, but I really did enjoy this presentation, and I hope you did as well. Thank you.